Hello again. NASA announced they're moving in, having sooner the launch of the Nancy Grace Roman Space Telescope. So I thought I'd do a little overview of it to people hearing about what is this thing and who was she, and just a few slides to cover the basic overview. And if NASA tasks me later on, the Space Telescope Science Institute or SETI, who has funding for these sorts of informational presentations, I can show them this, and if they want more, I'll do something with more minutiae to it, as I'm known for. So the Nancy Grace Roman Space Telescope is named in honor of the NASA former chief of astronomy back in the days. And this was formerly known as the Wide Field Infrared Survey Telescope, or WFIRST. NASA space telescopes often get a very technical name for them with an acronym, and then later on they'll give it a name, like the James Webb Space Telescope wasn't always known as that. And in this case, the Roman wasn't always known as the Roman. It was WFIRST. It's primarily infrared, although it does have like a little slice of some red, but not broad spectrum like a Hubble Space Telescope. There's no UV, no ultraviolet, and there's no radio astronomy observing. It's going to be launched on top of a SpaceX Falcon Heavy. That's the 3 Falcon 9 strapped together. It's going to be launched to Lagrange point 2, as other things are. It's a very convenient place. It's not specifically to L2 itself. It will have a virtual orbit, an elliptical tilted orbit about L2. And that means that there's some places it won't ever be able to look back at, like the sun, the earth, or the moon. They were going to launch it sometime around May of 2027, but it passed its tests and they can package it up and ship it off to Florida from Goddard Space Flight Center. And so they're going to try and launch it September of 2026. So here's your overview. The thing that people don't quite understand about when you launch a telescope out into space, and now it can look anywhere. No, it can't. When you launch something to an L2 orbit, you don't want to damage your highly sensitive infrared instruments. So it can never look back towards the moon or the earth or the sun in particular, because it'll be just too bright and it'll destroy the instruments. They're that sensitive to infrared light because they're trying to pull light from things in deep space like exoplanets. And they have to be super sensitive, but they still need power. So the solar panels need to face the sun, and they still need to talk to Earth. So the large parabolic communications dish antenna needs to be pointed towards Earth. And if you look at the diagram on the right, that means that, well, it's never going to tilt down or backwards. So it's going to basically swivel about this point, and it's not going to look outward, which I thought was a little weird. But remember, it's at L2, and L2 swings around with the Earth throughout the year. So they'll only be able to look at certain parts of the sky at certain times of the year. And they're only going to be able to swing this way and not this way, which the James Webb Space Telescope can tilt a little bit. I think it's like 12 degrees out either way. And if you remember the James Webb Space Telescope, it had this flap on the front, and they could adjust the position of the flap. The flap was not to like shade something. The flap was because in the elliptical orbit about L2, as it goes one direction, the gravity of the Earth and the moon and the sun pull it that direction. But as it goes the other direction, it needs something to push it back. And they actually use the solar wind, the particles and the light, radiation, reflection, pressure, pushing against that flat panel. But they found out the panel doesn't really need to move as long as you can rotate the spacecraft to point it in the right direction. So the sun shield, which protects the instruments from sunlight, moonlight, and earthlight, doubles as the wind vane, so to speak, for solar wind. So I thought that was clever of them to do that. Imaging. You'll often hear discussions of how big an imaging array they have. Well, this one's got a big imaging array. The actual aperture, that tube on the front that's how much light can come in, that is 2.4 meters or 7.9 feet in diameter. This is primarily an infrared telescope, although it sort of scooshes over a little bit towards red. It doesn't get into mid-infrared or deep infrared. It's just near infrared. They have something called the wide field instrument. It has 18 cryogenically cooled imaging chips. And you can see in the picture on the right, the individual chips. Now, what you might not pay attention to is there's a gap between all the chips. You can see that like the chips on the right and the chips on the left, they're abutted. They're like together, like 17 and 18 are abutted together. So the gap between them is rather small. But then the chip above it is higher up because they wanted a wider field of view. So they'll actually interpolate pixels that they don't receive to fill the gaps. They could have put them all together, but then the field of view would have been smaller. Each one of these chips is 4096 by 4096, so it's 4K by 4K. The field of view is 0.4 degrees by 0.8 degrees. So 0.4 degrees by 0.8 degrees, it can see about a full moon width in the narrow, and in the other axis, it's about 2 full moons across. A single collective image across all these chips is about 300.8 megapixels. The individual pixels within one of those imaging chips are 10 micrometers across, and the resolution at full view is 0.11 arc seconds per pixel. So they can take high resolution images of very, very small things. And when you have that much data flowing through, you don't want to send the massive amounts of raw data down to the Earth. You want to do some of that processing on the telescope. So much like the James Webb Space Telescope, it has a section of electronics that are not super cooled. They're just protected from temperature changes out in space. They're called the warm electronics module, and they have smarts there. So it'll be doing the alignment and the tracking and gathering the image data, and then it will be doing some amount of onboard post-processing to create the images, much like the James Webb Space Telescope. All the processing that they need for the basic imaging can be done on the telescope, and then they just send down the finished goods. It has filters, because if you're going to do things like spectroscopy, you want to be able to receive light in certain groups or bands, and then you look at the spectroscopic signature in that small area. So when you put a filter on, it may slide the frequency response of your imager, and it may actually narrow your imager so that maybe you only get one chip's worth. But all you're looking for is just the wavelength signature of some chemistry in some distant star or exoplanet's atmosphere. So it has 8 positions for filters. And if you can count, there's only 7 filters. One of the filters is no filter. So that's how you get to 8. You have 7 band filters and a no filter. And if you can't convert microns to nanometers, I've already done that at the bottom. That's the nanometers conversion is down at the bottom of the graph there. And if you know wavelengths, you'll know that, well, if I get down to 390 nanometers, isn't that ultraviolet? Well, it doesn't get to 390. It gets down to 490, but it's not that sensitive in ultraviolet towards the deep blue end. It's more sensitive towards infrared, but if you look at the axis along the bottom there, it gets out to 2890, but there's no filter that will take you to 2890. That's because it doesn't get to medium infrared or deep infrared. It's just near infrared. And it has a coronagraph. What is a coronagraph? A coronagraph is basically, you want to take an image of something that's dimmer than a star so you can see like planets around that star. So you need to blot out or occult the brightness of the star in order to see the dimmer things. When it does this, it doesn't need to look like at a big chunk of sky. It wants to look at a really small area of sky, and right next to it, either on the left or the right side of it, will be the star. So it wants to blot out that completely so it can see little dim things next to it. So Um, this telescope will have the ability to observe something that is 100 million times fainter than the host star of that solar system. And it is 1,000 times more sensitive than any coronagraph we currently have in a space telescope. And this is the first coronagraph they will ever send in space that is what is known as an active coronagraph. So when a typical coronagraph is, you set the parameters for what image you want. It's called a passive coronagraph. Like, I want a disk this big here, and then I expect to see the exoplanet over here on the side. This one is an active coronagraph. So as it's taking a picture of the exoplanet, if the area being blocked out isn't enough, there's too much light coming in, it will dynamically change the shape of the occulting coronagraph disk to blot out more of the star's light to make it easier to see the dimmer exoplanet. Fascinating. Here's the spectrographs. There's two of them. There's GRISM and PRISM. GRISM is a grating, and PRISM is a prism. The reason why they need this is because they can get different chemical signatures as either discrete or continuous. A prism, you can get more continuous. A GRISM, you can get more discrete. And you can tell that by the ranges, 1.0 to 1.93 versus 0.75 to 1.8. And this is in near infrared. And if you look at the wavelengths along the bottom, it can't get into deep infrared. And just for reference purposes, if you're thinking about, well, infrared, how close is that to red? Well, red, visible red, is 740 to 630 nanometers. And this doesn't get down into red. So this is just an overview. As some might say, too much minutia, but that's just my nature. If you want to see something I did back in 2021 on the James Webb Space Telescope, when we actually had somebody from the Space Telescope's Science Institute sort of moderating what I was saying, he didn't have anything to say except at the beginning to introduce himself and at the end to thank for the presentation being done. But that's an hour and a half long presentation between the presentation and comments. This one's obviously shorter. So in summary, oh, I spelled it wrong. Look at that. The Rome Space Telescope, the Roman, is going to be launched to L2, hopefully in September aboard a Falcon Heavy. And it will be primarily infrared. The colors won't be visual range. They'll be mapped. And for science data purposes, for contrasting things, they can false color them, primarily near infrared. This will be the first active coronagraph, and they'll have two spectrographs as well. The aperture, the diameter of how much light comes in, is an improvement over the Hubble Space Telescope. But remember, the James Webb Space Telescope unfolded the mirrors, so the aperture of the JWST is larger, but this is bigger than Hubble. Given that we have decades of newer imaging chips, the 4K by 4K and having 18 of them, obviously the total pixels and the pixel resolution, the density, is better than the Hubble, but the field of view is better than the Hubble as well. But I would say you can't compare these to the James Webb Space Telescope, which has a broader spectral vision and higher resolution and larger aperture. What it doesn't have is the active coronagraph, which is going to allow them to see exoplanets using gravitational lensing of the parent star, which I think is fascinating. And the Hubble HST can also see deeper into infrared and some ultraviolet as well as visible. Here's another thing that's interesting. When the James Webb Space Telescope is imaging, it shuts off its communications with Earth, because as the probe is doing its elliptical path and doing its imaging, keeping the parabolic dish antenna pointed back at Earth to maintain the signal means you got to move the antenna. And moving the antenna wiggles the entire spacecraft. This has the same problem. It's got that giant parabolic dish antenna. So while it's imaging, just a little nudge on the antenna because it's going around L2 will jitter the image. So how do you capture to avoid the jitter? Well, you shut down communications, you take your image, and then you resume communications. that says the maximum amount of image you can store is limited by the flash memory size of whatever you put on there. I have yet to find that for the Roman, but for the JWST, it's a little over 1 hour's worth of data. So if they want to, if you see like this is a deep sky long duration image, it's about an hour, but it's a 30-day exposure. No, it's a little over an hour exposure, and then they resync, do a transfer, get it out of the system, and then they align back up again and do another about an hour. So it's 30 days worth of 1 hour exposures stacked up. So given that this is a much newer telescope than the Hubble, and it's even newer than the James Webb Space Telescope, the electronics on the inside are smarter and faster. So it'll be smarter and faster than JWST, but in the ballpark, but it'll be far faster and smarter than the Hubble. Now, the Roman is, at least as far as the active coronagraph, is an improvement over JWST and HST. But since both of those are still operational and still generating science in bands, wavelengths that don't replace this, the Roman is not a specific replacement for either the HST or the JWST. So if you hear funding discussions about, well, we've got the Roman now, we can't afford to have 3 telescopes running, because remember, they want to get rid of the X-ray telescope because we can't have 3 telescopes running. Yes, you can. It just costs more money, but it's not that much more money per year because they're already up there. You don't have to launch them again or build them again, but they're already producing science, so they're cheap to keep, comparatively speaking. Now, what is the purpose of this particular telescope? Why do we need another one? This is going to be observing exoplanets. That's planets around other stars, and it's going to be observing them using gravitational microlensing. So some of the focus magnification will be courtesy of the gravity of the parent star. And since it can see things farther out into space, it can judge how old things are. So maybe some of those early in the universe red dots that the JWST can't quite explain, if the Roman takes images of them, there'll be different kinds of images, different spectral analysis. Maybe you can say, well, you think they're old. They're actually older than that. You think they're just the core of galaxies. There's actually stars in there. So universe chronology and also dark energy effects. Now, dark energy effects as opposed to dark matter effects. Dark energy effects, the stuff that's pushing the universe apart. Yes, you're going to be able to, with the Roman, spot something and then come back a year later and see where it is. So you can judge how much it moved down to a tiny fraction of an arc second. And that will allow you to say, well, the only reason it's moving out that far is because of dark energy. And if you notice such things, I have a new acronym up there, AAAS, the American Association for the Advancement of Science. They asked me to join. I said, sure, why not? And then links.
They asked you to join? It usually was the other way around. Wow, congratulations.
I get an email from them. Would you like to join? Okay, how much? I think it was $35 or something. I said, okay. Comments? Questions?
Yeah, James Webb, they had an extreme concern about temperature controls and stabilization.
Yes.
Do they have that with this? It doesn't look like they've got anything to keep it cool.
They have a different kind of cooler. Yes, they do have helium on board, but they have a regenerative cooler whereby they don't have to pay, they don't have to consume as much helium. They can essentially regenerate the chill electronically. They can't do that while they're capturing, so they have to get the temperature down, and then they stop the regenerative cooling, and then they capture, and then they can resume the regenerative cooling. So they monitor the temperature of the imaging array pretty closely, and so far all of that's worked. The only thing that I've heard that was a problem was essentially micrometeoroid dust as the Earth plows through a meteor trail or a former comet trail. That fine material does affect the overall brightness of what it can pick up. It doesn't get on the imaging chips themselves. It gets on the beryllium reflectors. And yes, it is by a numerically calculatable value, not getting as bright an image as it used to. Is it affecting the science? Not significantly, no. Yes, it's minutia that I pay attention to.
Yeah, they call this wide field. It's not wide field. It's very narrow.
A half a degree by almost 1 degree. That's a half a degree. If you hold your hand out at your arm, I'll do it with this arm because this one goes straight. If you hold it, your hand out, your little finger is a half a degree. It's strange to human physiology, but whether you have short arms or long arms, big fingers or little fingers, it's all proportional. So you hold your arm out at arm's length, and the width of your little finger is half a degree. Yeah. And that's the width of the full moon.
Field. That's wide field. It's
yes, because if you want to look at something like planets in our solar system, the smaller planets like Mars or distant planets like Pluto, you're looking at a tiny fraction of a degree by tiny fraction of a degree.
Yeah.
So if you can get to a half a degree by 1 degree, that's a wide field.
Yeah.
In amateur astronomy, they purposefully will buy wide field telescopes with a very low focal ratio. They'll try for like an f2 or an f3. And the reason for that is they get super sensitive cameras, well, at least as sensitive as sort of normal thermoelectric cooling can make them. And they want to take pictures of, as they refer to them, dim deep sky fuzzies. The Andromeda galaxy, if you look at that with your eye through a telescope, your eye is not that sensitive. So you're going to see maybe a quarter of a degree by a quarter of a degree. But with their sensitive camera that's been electronically chilled on their wide field telescope, that's what they call fast, it captures light and can capture it faster in the electronics, gathering more photons. They can get to about 2.5 degrees by 2.5 degrees. The Hubble Space Telescope, since it's in low Earth orbit, when it does imaging of the Andromeda, it can get to 3 degrees by 3 degrees. So the Hubble Space Telescope has an ultra wide field capability, but sometimes you can't tell because what they'll do is they'll take a bunch of little pictures, send the pictures back down to the Earth, and stitch them together to make a wider field than the individual image field. And they can do this with pretty much any telescope. When they produced the James Webb Space Telescope and now the Roman, they said, sending down the individual pieces that then you get stitched together on the Earth, that's a lot of data moving. And it was with the Perseverance rover on Mars that they found, why don't we just put that software into the distant space probe and have it gather the data and stitch it together and do some processing on it and then send us down the final result, because that will be a lot less data.
If they're working on looking at images that have gravitational lensing, that's already a hell of a job to try to stitch images together. It's already
but they won't. What they'll do is they'll have one of the 4K by 4Ks aligned with where the exoplanet is, and they'll have the rest of the entire array occulted by the coronagraph. Because all they want to see is, because the exoplanet's going to be
the distortion that the lensing could produce, then they have to stitch images together that are already distorted.
They won't be like football distorted, like amateur astronomy. They'll be positionally distorted. Like instead of looking for the exoplanet here, the exoplanet will be over here, because the photons will be pulled towards the gravitational field of the host star.
Not ballooned or anything. Yeah.
So what they'll typically do is, once they find an exoplanet, they'll take a few images to calculate the orbital duration, and then they'll plot where the ellipsis of the orbit is farthest out at the lobes of the orbit. And that's where they'll do their serious analysis is there. But they can't look there because the math will say it's going to swing out to here. But it's not going to be there. It's going to be a little closer to the star than there because the gravity will have pulled the photons coming off of the reflected atmosphere of the exoplanet. So the micro lensing is something they have to pay attention to, but it's a bit of a nuisance.
Sure, it's a nuisance. Boy, a lot to consider.
It's the minutia. Modern astronomy and physics and chemistry, we live in a world of minutia.
It must take years to discuss all this.
It does. They didn't come up with the Roman telescope yesterday. I think it's been 11 or 12 years that it's been in the works.
Monroe, Google's AI says that the Roman's solid state recorder has a 1.1 terabyte capacity.
Yes, but it has 18 4K by 4K imaging chips, and they grab it in 3 colors. So the terabyte sounds like a really good amount of space. When you start divvying it up, like, okay. So I would say if they can get on the order of a 1 hour exposure, they'll be doing really good. But yes, thank you for that. Oh,
Sure.
You use Google AI for that?
I did some Googling and I found out that the storage is called, they call it SSR, solid state recorder. So then I Googled Roman telescope SSR capacity.
Yes.
And it came up with that.
And it does that in just 1 or 2 seconds. It's amazing.
Yep.
Okay. Any other comments or questions? Like I said, this was going to be a short one and I'll stop recording. Okay.